Hello everyone. Today I would like to present our research entitled Implementation of a Kinetic Algorithm Method for Stochastic Model of COVID-19 in Indonesia. In general, our research discussed the implementation of the genetic algorithm method on the stochastic SIR model to represent the spread of COVID-19 in Indonesia, especially from January to July 2021. But first, let me introduce our team. Our team consists of Pak Akam, Pak Sentot, Bu Endah, and myself, Aldi Eka Wahyu. Here is the outline of my presentation. Let's begin with the first part. The first case of COVID-19 was reported on December 1, 2019. COVID-19 has caused millions of deaths worldwide and long-term health problems in some people who recover from the disease. COVID-19 cases in Indonesia, especially in 2021, shows two waves. The first wave appeared in January and the second wave in July, with the number of infected individuals reaching the highest peak. From various scientific fields, including mathematics, the study was conducted to provide advice in handling and preventing the spread of COVID-19. In mathematics, mathematical models for the spread of disease are often constructed from a compartmental model, one of which is the deterministic SIR model. In further research, the compartmental model is expressed in a stochastic model form. The stochastic model provides a degree of flexibility in real conditions compared to the corresponding deterministic model. The parameters of the model are very sensitive to fit in the real problem. There are several methods to solve this problem, namely Kalman filter, kinetic algorithm, control theory, single parameter estimation approach, etc. Among these various methods, kinetic algorithm is one of the popular methods for optimization because of its easy implementation, low computational time, and fairly accurate results. In this paper, we propose a stochastic SIR model using the kinetic algorithm to represent the spread of COVID-19 in Indonesia. We perform simulations to obtain predictions for the next 7, 14, 21, and 31 days, which are compared with the actual data. Here is the deterministic SIR. Here is the deterministic Here is the deterministic SIR compartmental model. The definition of the S, I, and R compartment are shown here, while the relationship between compartments is shown by this compartment diagram. The SIR model is described by the following system of differential equations, where beta is the infection rate and gamma is the removal rate. We consider two references in the stochastic approach to the model, i.e. Gray et al. And Rihan et al. Both involve Brownian motion as a randomness factor. Gray et al. Stated that environmental factors alter the deterministic infection rate to a random variable involving a Brownian motion, while Rihan et al. Stated that environmental factors affect all individuals of the population, thus a Brownian motion is added in every equation. We combine those two stochastic approaches and apply them to the SIR model. We get the following differential equation in the continuous form. Next, we discretize the model and get the following discrete form of the model, where delta t is the step size. We will estimate beta, gamma, sigma 1 until sigma 5, and also S0 because there is no information about how many healthy people could be infected initially. Next, the kinetic algorithm. A kinetic algorithm is a heuristic search and parameter estimation algorithm inspired by the theory of evolution by imitating the natural selection process. A solution to the problem to be solved is called an individual. The number representation of an individual is called a chromosome. In our case, the individual are the state variable of the model, while the chromosomes are the set of model parameters that are to be estimated. In GA, each individual has a fitness value, which is a real number that states how well an individual is to the problem. Parameter estimation in GA includes 4 states, i.e. generate initial population, selection, crossover, and mutation. Here is our GA implementation. We first generate 300 individuals. The chromosome representation is shown here. We use MAPE average as the fitness value because it does not depend on the scale and is easy to explain. So our objective function is to minimize this value, where n is the number of data, AI is the actual data, and PI is the estimated data using stochastic SIR model. For the selection sim, we use the roulette wheel. For the crossover, we use uniform sim using these two equations. For the mutations, we use random addition or subtraction of a gene. Finally, we select the crossover rate and mutation rate of 0.8 and 0.1 respectively. Here we show the flowchart of genetic algorithm. The input is COVID-19 data and the output is model parameters and corresponding MAPI values. Experimental results. So next, this is the dataset that we use in our research. It is obtained from Indonesia's COVID-19 response data from this website. The data consists of 5 columns. We use the second and the last columns as the infectives and removed compartment. The data shows 2 waves. The number of active cases was increasing in January, but began to decline on February 6 and lasted until the end of May. In early June, the number of active cases began to increase again and rose sharply in July until the end of the data period. The GA implementation resulting MAPI values shown in this table. The MAPI values of IT range from 8.24% to 10.80%, while the MAPI values of RT range from 1.17% to 2.18%. The smallest or best MAPI average is from trial 7, which is 5.21%. The figure on the upper right shows the estimation of the infectives, the red line, compared to the actual data, the black line. It can be seen that GA can follow the sharp increase in the actual data, i.e., can detect the second wave, although there are some fluctuations. The figure on the lower right shows the estimation of the removed, the green line, compared to the actual data, the black line. Here, GA can provide accurate estimate. The resulting parameters in the parameter estimation process are shown in this table. We then choose the resulting parameters from trial 7 to obtain predictions for the next 7, 14, 21, and 31 days. In making prediction, we use the parameters to generate 10,000 paths of the infectives and the removed. In making predictions, we use the parameters to generate 10,000 parts of the infectives and the removed. Next, we calculate the MAPI values of each path and choose one with the smallest MAPI values. The results are shown in this table. We get very precise predictions for 7 days as the average MAPI values are below 1%. For the 14 days predictions, we get precise predictions because the average MAPI values. In making predictions, we use the parameters to generate 10,000 paths of the infectives and the removed. Next, we calculate the MAPI value of each path and choose one with the smallest MAPI values. The results are shown in this table. We get very precise predictions for 7 days as the average MAPI values are below 1%. For the 14 days predictions, we got precise predictions because the average MAPI values are below 2%. For the 21 and 31 days, the predictions, we get the average. Check. In making predictions, we use the parameters to generate that 1, 2, 3. In making predictions, we use the parameters to generate 10,000 paths of the infectives and the removed. Next, we calculate the MAPI value of each path and choose one with the smallest MAPI value. The results are shown in this table. We got very precise predictions for 7 days as the average MAPI values are below 1%. For the 14 days predictions, we get precise predictions because the average MAPI values are below 2%. For the 21 and 31 days predictions, we get average MAPI values around 3% and 4% respectively. And up to 31 days prediction period, the parameters generated by GA can provide good predictions. However, it is not guaranteed to produce a good predictions for a longer prediction period because the MAPI values tends to increase with increasing prediction days. So here the conclusion. In this paper, A kinetic algorithm method is implemented along with the stochastic SIR model to estimate the parameters of the model. The parameters obtained provide good conditions. 1, 2, 3. In this paper, a genetic algorithm method is implemented along with the stochastic SIR model to estimate the parameters of the model. The parameters obtained provide good prediction for 7, 14, 21, and 30 days. However, good predictions is not guaranteed when the prediction time is more than 31 days. More complex models may be needed to better describe the spread of the COVID-19. Thank you.